Let's do the salinity budgets, and I just noticed that in the previous podcast I forgot to turn on the headphones, so the sound is coming through the computer audio, but I listened to it. It seems pretty clear, so I'm not going to re-record it, even though it would have given me a opportunity to remove the stupid mistake I made in where the sections were. Anyways, so how does salinity actually play a role in air-sea interactions and so on? Long-wave radiation is a modest function of emissivity epsilon, which we talked about when we did the temperature budget, which depends on sea surface salinity. Higher sea surface salinity results in lower long-wave radiation. Latent heat flux is a function of the specific humidity gradient across the sea surface delta Q, and the saturation vapor pressure of seawater depends on sea surface salinity as well. So higher sea surface salinity results in lower latent heat fluxes. Typically we don't worry about these things, they are too small. The time rate of change of SST or mixed layer temperature due to 1 watt per meter squared net surface heat flux Q net depends on the density rho of seawater, which is obviously a function of salinity and a very nonlinear function of temperature and salinity. Higher sea surface salinity results in a lower SST change. So where where salinity is high, the time rate of change of temperature can be lower for a heat flux perturbation of the same amount. The effect of QNet is also damped by the specific heat of seawater, which is a function of salinity. Despite its usual treatment as a constant, CP varies by approximately 1.4% across a typical range of sea surface salinity observed in the world ocean, going from 30 to 40 kilograms per grams per kilogram, or PSU. In this context, higher sea surface salinity results in faster sea surface temperature change. So you can see the compensating effects here of slower change because of net surface heat flux through these effects, and faster SST change due to CP dependence on density, but nonetheless we will leave it there. The mixed layer structure itself that we looked at as vertically homogeneous temperature with the thermocline meeting the deeper isothermal ocean, the buoyancy forcing, surface flux forcing, evaporation, precipitation, especially fresh lots of rain, can make for very interesting vertical structure. You can see here that salinity is much less stratified in the vertical than the temperature. So obviously salinity is lower near the surface here and increases towards the deeper ocean, as opposed to the temperature which is higher near the surface and decreases towards the deeper ocean. So freshwater forcing, obviously if you go to evaporative regions like the subtropical gyre, this can be different, but in the tropics this is quite common. So this different stratification in the vertical between temperature and density gives us a vertically homogeneous density that is different than homogeneous temperature, and this is referred to as a barrier layer because it acts as a barrier to surface cooling when there is entrainment mixing. Remember, we said entrainment is when the mixed layer depth changes and the waters below are entrained into the surface mixed layer, which is obviously this layer here, because it's the definition of vertically homogeneous density and temperature and salinity together. So the isothermal layer, when it is deeper than the isopycnal or the constant density and isohaline layer, you get a barrier layer, and it acts as a barrier to cooling the sea surface due to entrainment. So in some sense it decouples the dynamics and the thermodynamics. You can think of dynamics as processes that deepen the mixed layer, for example, and thermodynamics as the heat budget terms that change the temperature. Okay, so it turns out that the barrier layer can play a critical role in many places, including under the hurricanes, and let them get more intense when there is a barrier layer, because the entrainment doesn't cool the surface, and the hurricane gets energy from the ocean when that happens. Okay, so we can write the salinity content of the mixed layer just like we wrote heat content as rho times the mixed layer depth times average salinity, and then we can write a salinity budget equation as del ms del t equal to rho h ds dt, assuming h is we are doing at a place for a given h. So that obviously depends on the surface fluxes of salinity. Even though salinity is not exchanged, you can change salinity by evaporation and precipitation, so that's the freshwater flux, plus the ms import rate minus ms export rate. Okay, think of those as the advection terms that we talked about. So del S del T here then is dependent on E minus P, evaporation minus precipitation divided by rho H times S. So the amount of water exchanged at the interface is multiplied by salinity to get the impact of the net freshwater flux on the salinity budget over mixed layer depth H for given density rho, minus V dot grad S, which is the horizontal advection terms that we talked about. Here is freshwater flux E minus P in meters per year, so you can use these units and convince yourself that E minus P can be either in obviously kilograms per meter squared per second, or you can convert it to a meter per second in terms of the amount of water. Like rainfall we measure in millimeter per day, right? So it's a similar thing here. Meters per year, averaged from 1984 to 2009 using the Hui OA flux and GPCP, which is the Global Precipitation Climatology Project data sets, and profiles of E, P and E minus P zonally averaged, so zonally averaged across all longitudes. B is the same as in A, but it is the sea surface salinity, so you can see the similarities. I'll talk in a minute, but this is only averaged for the Aquarius data set from 2012 to 2014, and here we have the zonal mean sections. So let's look at these. Again, we saw this before in terms of salinity. We talked about subtropical gyres, the contrast between the Atlantic and other oceans, and river runoffs and precipitation, ITCZ, freshwater here from the Bering Strait and other processes, and the contrast here, and so on. If you compare E minus P, obviously subtropical gyres are net evaporative regions where the Hadley cell comes down because they are supplying water to the ITCZ and also northward. And of course this is the cold tongue subtropical gyre evaporative region as well, and you have the SPCZ and the ITCZ and so on, where evaporation is less than precipitation, so you have negative numbers here again in meters per year. Okay, and you can see the stark contrast here again in E minus P, which corresponds to the salinity as well. So if you look at the zonal mean meridional sections here, you can obviously see the E minus P positive regions and E minus P negative regions with the high latitude storm tracks, as well as the ITCZ, tropical intertropical convergence zone, and you see evaporation high here, low here, low here, high here, and low here, and precipitation of course is high in the ITCZ region, low in the subtropical gyres, and higher in the storm track regions, which has a hemispheric asymmetry as well. The net result on the SSS of course is that the zonal mean here produces low salinities at higher latitudes, high salinities in the subtropical gyres, and low salinities in the ITCZ. So evaporation obviously is related to latent heat flux with the latent heat of vaporization, latent heat of evaporation. So E is QLH divided by LV, we already saw that del S del T, if E minus P is 0, can be just the horizontal fluxes within the mix layer, which is similar to what we had considered for temperature. So U ds dx, V ds dy, and W ds dz. Again, we have to be careful with W because you have exchanges at the surface in terms of fresh water, which is different than temperature, and we need to worry about entrainment at the bottom of the mix layer like we did for temperature as well. So this has to be done very carefully. There are ways in which these are done where you can convert the salinity flux to a vertical velocity at the surface and so on and so forth, which we will not get into. We'll just simplify it and write it as del S del T equal to minus U ds dx plus minus V ds dy minus W E delta S over H, as we did for entrainment, plus K del squared S, which is the eddy diffusivity term, similar to the eddy diffusivity term we had added for temperature. Thermal diffusion and haline diffusion are very different in order of magnitude, which has consequences for how salinity gets mixed down and how temperature gets mixed down, and how that can create density gradients and density driven currents and so on and so forth. Looking at the heat budget terms, horizontal salinity advection, sum of zonal and meridional advection terms minus U ds dx and minus V ds dy are being shown here using surface velocities from SODA, which is a reanalysis product, simple ocean data simulation system, averaged from 1984 to 2008, and sea surface salinity from Aquarius dataset, averaged from 2012 to 2014. So we tend to mix and match things like this to do heat budgets and salinity budgets, which gives us a lot of understanding of the processes at large scales, but one has to be careful when you mix and match in this sense. The inset box marks the domain we will look at in the next slide of the figure 3.8. B is profiles of ocean mix layer salinity budget terms zonally average across all longitudes with spatially varying mix layer depth in the freshwater flux term based on a fixed density threshold criterion. So how do we actually estimate the mix layer depth? This is not a very easy problem. It is obviously dependent on the turbulent kinetic energy at the surface, which is combination of heating and cooling, freshwater flux, and momentum flux. So in general, there are models which are one-dimensional, and now there are more fancy models which also account for horizontal terms like the Langmuir cells and so on the mix layer depth. But in general, using data, it's diagnosed. So diagnostically, we compute it either as a temperature criterion where SST drops by 0.5 degrees over the mixed layer depth, or density drops by some amount like 0.03 kilogram per meter cube, and so on. So you have to be careful about those as well. So you can see the complexity of doing these, but nonetheless you can clearly see again where the advection terms will be strong under the ITCZ, at the subtropical gyres, at the fronts between ITCZ and the subtropical gyre, advection terms across the subtropical gyres and across the equator and the ITCZ here, lots of eddies here in the Southern Ocean, and the terms here again correspond to the E minus P and the salinity profiles we looked at before. And you can pay attention to see where the meridional terms are very large, where divergence of salinity is determined mostly by meridional terms here. For example, the trade winds converging into the ITCZ create strong meridional advection term as opposed to weaker and even opposing zonal advection term, and the terms of meridional and zonal advection can be similar but completely opposite in direction in some places and so on. So all these things have to be kept in mind. along with the freshwater flux written as E minus P times S divided by rho H, which corresponds to subtropical gyres, ITCZ, and so on. So salinity budgets are a tiny bit more complicated than the temperature budgets, but just get a good sense of how it is done. Finally, here surface currents from the simple ocean data simulation dataset averaged from 1984 to 2008, and sea surface salinities from Aquarius data averaged over 2012 to 2014 over this box here. And you can see how the currents in the ocean, these are the south equatorial, you are across the equator, so north equatorial currents, and then the subtropical gyres with the weaker currents and the convergence, bringing together salinity, so your strong advection of salinity across here meridionally and zonally, and you can see the fronts here actually related to also freshwater fluxes from the Amazon, Orinoco, and so on at the coasts of South America. And you can see how the subtropical gyre and the convergence create high salinities in the middle. Okay, the big thing to worry about in salinity budgets also is the river runoff. All that rain that falls on land eventually runs into the ocean. This paper looks at free running rivers, so it creates what is called a connectivity status index, where the index is high means the rivers are not dammed too much. When the connectivity index is low means that the rivers are dammed so much that the water may not be reaching the ocean at all, which happens over the Colorado River, for example, and the Columbia River, and so on. So you can see there are tons of rivers which all put salinity, as we saw in the salinity map. For example, the Bay of Bengal is very fresh, related largely to the river runoff as well as the rain. There is high river runoff here, there's high low river runoffs here, but Arctic has high river runoff. The Arctic water comes into the the North Pacific region here as well. The Amazon Orinoco plume is seen here, Congo Zaire here, and so on and so forth. Okay, so river runoffs are a big part of the salinity budgets, and even though they stick close to the coast, in some places they are advected far out into the open ocean. So this is a short chapter in terms of salinity budget. Now we will look at momentum budget, which is also very critical for mixed layer depth and mixed layer heat and salt budget, because mixed layer depth determines those together and is the critical heat content that impacts the atmosphere and the coupled ocean atmosphere interactions, as well as mixed layer thermocline interactions. So we'll come back and look at those. Okay.